Thank you very much for the introduction. Since I have 15 minutes to present a lecture, fasten your seatbelts. I'm going to talk a little bit about the practical issues of tunnelling in overstressed rock, and having listened to the previous lectures, the theme I'm going to emphasize is one that was stated by my late friend Pierre Lund from France, who said it is the duty of an engineer to judge soundly rather than to compute accurately. So that's the underlying theme of what I'm going to talk about. If we look at the range of problems that we can encounter in tunnelling, I've tried to classify these into an array showing, starting with massive rock. I'm going to figure out how to work this. Massive rock up here at low stress and increasing stress on the vertical scale, and going down to heavily sheared rock on the right-hand side. Ideal tunnelling conditions are typically those illustrated by the green ellipse there, and fortunately these are fairly common around the world, and there are many, many hundreds of kilometers of tunnels successfully excavated in that zone. Unfortunately, as urban populations become more dense and as we run out of easy-to-mine space, we're forced into working in the other areas of this plot. And one that I'm not going to discuss in this lecture is where we have structurally controlled rock masses, rocks with joints, faults, fissures, at low stress, where the problem is understressing rather than overstressing. And I'm not going to discuss that area in this presentation. I'm going to deal relatively briefly with this one, where we have massive rock at increasing depth. And with the base tunnels in the Alps, with deep tunneling in the Andes, in the Rockies, in the Himalayas, we're getting increasingly involved in working in this field. And particularly if we get into tunnel boring machines, where we have to deal with the complication of high stresses and a tunnel full of machinery. I'm going to spend very little time in this area, but it's probably the most exciting area for the future of rock mechanics, where we have, as John Hudson has pointed out, a combination of structurally and stress-controlled phenomena superimposed on one another. And it's a huge subject in which a lot of work is going on, very exciting work, and I will just touch very briefly on that. And then finally, right at the other end, tunneling in materials which are heavily sheared, tectonically deformed, and where ductile type failure is a much more common phenomenon and a difficult one to deal with. Starting at the massive hard rock end, we know from experience that if you look at the stresses around an opening, and I'm just taking an elastic example here, you calculate the maximum principal stress on the boundary, assuming that you know the in situ stress field, which, as John has pointed out, you don't always do. Failure starts at about 0.45 of the uniaxial compressive strength as determined in the laboratory. And so if you look at that at the practical consequence of that, the rock behaves basically elastically in the grey zone here. And as you move up the ratio of maximum boundary stress to uniaxial strength, the problems have become more and more severe. So first of all, you might have very small, thin spalls forming around the opening, increasing spalling size, massive failure and disruption, and finally rock bursting. And it becomes extremely difficult to support in the situation where your in situ stresses are, let's say, more than 1.5 times the strength of the rock. Derek Martin has done a lot of work on the failure processes in particularly granite, and this is in relation to the Atomic Energy of Canada Underground Research Laboratory, where we had very good details on the rock material. It's a mass of granite, on the in situ stresses, and the laboratory testing shows that you have failure initiation at about 40% of the uniaxial compressed strength, determined either by acoustic emission measurements or strain measurements, and an increasing generation of cracks until about 70 to 80% of the uniaxial strength, which probably represents a reasonable estimation of the long-term strength of the material. And this applies for a great variety of rocks. If you look at this plot here, you'll see I've got uniaxial strength on the horizontal axis and crack initiation stress with 0.42 being the ratio, and over a very wide range of strengths. So this type of brittle spalling we see in all kinds of massive rocks, including some of the rocks that might surprise you, some of the strong shales and so on, which you would think would be much more ductile. The process of brittle failure is a complicated one because in going through from uniaxial tension to triaxial compression, you go through a whole range of failure processes, failure directions, and it's absolutely essential that all of these be incorporated into numerical models. And we're not very good at that at the moment. We have lots of models out there. Some of them are more pictorial than real, and you have to be very careful that you don't get fooled by the pretty pictures of modern computational graphics. But we're working on it, and there's a lot of work going on, I think, that's beginning to capture this multifaceted failure process. This is from the Atomic Energy of Canada site, where you had quite deep spalling around the tunnels in granite. And here is an attempt to model this numerically by Professor Mark Diedrichs. And the depth of the spall and the lateral extent of the spall is fairly well captured, but very poor representation of the volumetric changes that occur during spalling. That's a continuum model. Here is a discontinuum model that I've done myself by progressively inserting failures and reanalyzing the model. So there are about 40 models in that picture there, and not bad, but again, the representation of the volume changes are currently very poor, and that's something we have to work on. What we do know from a practical point of view is that the depth of the spall is very closely correlated with, again, the maximum boundary stress over the uniaxial strength. So that from observations all over the world, and these are observations from mines and tunnels all over the world, this again is a fairly tightly defined process. What we do also know is that you cannot stop this failure. Once the rock is overstressed, it's going to fail. That's a given. But you can control the behavior of that rock relatively easily, because you don't need a lot of force in order to throttle the development of the spalling. So that simple mesh and rock bolts tend to work pretty well for many spalling situations. This is a relatively small spall held by rock bolts and mesh. This is very high stress in Chile, where rock bursting is an issue and where a cable lacing has been used. So in addition to the mesh, you have these cables anchored on a very firmly embedded pin, and giving a lot of ductility and support to the rock. Also in the rock bolting side, the rock bolts with a high yield capacity so that you can get a large deformation while they maintain the load. And that applies to bolts like Swellex or cone bolts, which are a special South African design of bolts that slide in a ductile way. These are all necessary tools in order to control the process of brittle spalling. This is an interesting tunnel under construction in Chile, in Peru at the moment, the Olmos Tunnel, 2,000 meters below surface through the Andes, and it's 13.9 kilometer, 5.3 meter diameter TBM driven tunnel, driven by a open face TBM with constant rock bursting. I'm visiting that tunnel next month. I had an email yesterday saying that they are having to do stress relief blasting ahead of the face because of constant rock bursting. And yet, in spite of that, they have successfully supported it with what are clearly very light steel ribs. These are 160 millimeter steel ribs, spaced at 1 meter, installed under the finger shield, and wire mesh. And in spite of the bursting problems, the contractor for the first 5 kilometers averaged 22 meter advance rate per day. So we have a lot to learn about working with TBMs in spalling conditions. If we look at the transition from massive rock to jointed and heavily jointed rock, we go through a process whereby adding one joint set, we end up with a highly anisotropic system. 2 joint sets evens it out a bit, and many joint sets make it a pseudo-homogeneous material. But this area where you have relatively few joints can be enormously important in some aspects of engineering. This is a 3-dimensional, 3-deck model of a TBM going through a jointed rock mass under high stress, or under stress. And the issue here was what kind of blocks are loosened and can fall out at the face, because the TBM cutter needs a good clean bite at the face, and if blocks fall out, they have to be crushed before the machine can actually do any cutting. And so this is an illustration of some of those blocks that have fallen out. This is not a trivial exercise. The numerical models, fortunately, as John said, are becoming more available and more sophisticated, but you really have to switch on your brain before you switch on your computer in order to use these models, because they need a lot of very careful interpretation and a lot of engineering judgment. Probably one of the most sophisticated of these models is the synthetic rock mass developed by Peter Kundl of Itasca. This is an industry-sponsored, mining industry-sponsored program, and the first level of input is the structure network, the three-dimensional rock mass structure, and then the individual rock pieces are modeled by, in this case, a particle flow code, and that together gives you a rock mass where both the discontinuities and the intact pieces are modeled simultaneously. And the sort of things that are beginning to come out of this study are, for example, the scale effect in rock. So you're looking here at 20 meter, 50 meter, and 100 meter size samples, and as you would expect from just thinking about it logically, a significant drop in strength. The problem with this model is the computational demand is huge. These models take days to run on even the most powerful machines, and so what we have to figure out with time is what can you leave out and still obtain usable, practical solutions. And I would see we have a 5 or 10 year period ahead before these models become really useful everyday tools. What they do provide, though, if you think ahead, is a means of calibrating some of the empirical classification-based processes that we use today, because many of those are very difficult to calibrate. So these models offer the promise of calibration, if not ultimately replacement of those tools. Coming now to the semi-homogeneous rock mass to which these classification-based systems can apply, I start with the heavily jointed Panguna andesite, which formed the basis of the Hoek-Brown criterion in the early 80s, late 70s. And this is a very strong rock, but with something like 7 intersecting joint sets, very closely spaced. And at the time, we were looking at the design of a 1,000-meter high, open pit mine slope, and felt at that scale, this could be treated as a special kind of soil with interlocking granular blocks. And at the other end of the spectrum, this is in Taiwan, where the rock has been so tectonically deformed that the structure is effectively destroyed. In Greece and in many parts of the Alps of Europe, you have Flysch, which has been very severely tectonically deformed, and where, as a reasonable approximation, this can be treated as a homogeneous system. This led in Greece to the development of, although this one is for Venezuela, of a classification system to try and describe in a qualitative way how the tectonic forces have changed the rock mass behavior. And if you look at the estimation of rock mass properties from classification, they all follow exactly the same principle. The mathematics are different, but basically I've plotted a number of them here, and there are many others, which say that as the rock mass decreases or increases in quality, the rock mass strength, if you think of it, of the strength of a uniaxial, the uniaxial strength of a block, will decrease with decreasing quality, and this similarly with modulus. And in order to utilize that in an engineering sense, if you know what the rock mass strength is, you can estimate the friction and cohesion. You have two unknowns, but you know that for many cases, the friction will be around about 30 degrees, so you can estimate the cohesive component. The mathematics can get a lot more complicated, but the fundamental approach is the same for all of these systems. And what that enables us to do is to make some useful predictions. This is a plot of the potential for squeezing in tunnels where you start here with very little squeezing when the rock mass strength is equal or greater than the in situ stress. And as the in situ stress increases, you get increasing deformation until you get extreme squeezing problems, as I'm going to describe in a moment. For the Yacabu-Kibo tunnel in Venezuela, this tunnel started in 1976. It is 25 kilometers long at a depth of up to 1,200 meters through the Andes in Venezuela to bring water from the dry Orinoco, from the wet Orinoco basin to the dry side. Finally, it broke through in July of this year after 33 years of mining and huge problems of squeezing, but it's finally through now. This is a picture of the graphitic phyllite, which is the rock mass that gives all the problems there, and you can see that it's hugely tectonically deformed. In the early days, in the 1970s and the 80s, really there were some very poor decisions made on tunnel shape and support types, and in particular attempts to use horseshoe-shaped tunnels, as you see here, created huge floor problems. The connection of the invert to the walls always broke. You had the floor heave and then finally disintegration of the tunnels. That's one of those tunnels, one of the horseshoes that has collapsed almost completely and is being remined. Fortunately, the remining is pretty simple because the stresses have now been dissipated, and so you can put in a relatively light concrete lining. The principles of supporting in this kind of tunnel are relatively well known, so I'm not going to dwell on this. If you look at the convergence confinement curve, You need to put your support in early, as close to the face as possible, because you need to protect the workers. This is very unstable ground to work in. But if you put your support in early, it's going to be overloaded. So you have the problem here that the capacity of the support is overcome if you put it in too early. And the trick is to put the support in, but not to activate it until you need it. And there are many systems to do this, depending on the geometry of the tunnel and the amount of deformation that you need to absorb. Later on this morning, you will get a lecture from Professor Barler, who will talk about a system used on an exploration tunnel or an access tunnel in France. And I'll leave Giovanni to tell you about that. In the case of Yakambu-Kibo, we needed to accommodate large displacements, and I mean very large. And so the very simple system was developed where, first of all, we said no more horseshoe tunnels, everything has to be circular. And it's constructed in this way that you start off with a very thin layer of shotcrete just to seal the rock. You then put in steel ribs, steel sets with 2 open joints, and these are literally open 30 centimeters each, which gives you a total closure of 20 centimeters before they lock. These are embedded in shotcrete, except for a window of about 1 meter width, which is left open until the tunnel has advanced about 15 meters, at which stage either the sets have butted together and locked, or you close the tunnel with shotcrete. And then a final layer of shotcrete goes on the inside to give you the total lining, which for most of the tunnel was 60 centimeters of shotcrete. Here you see again the graphitic phyllite at the face, and here are the windows in the steel sets with reinforcement for the inner lining in place. They were very simply constructed on site and a fairly crude sliding joint, but they did the job effectively for this particular application. As I say, there are many other systems. Professor Wolf-Schubert has developed other systems, and there are others around that do this late engagement of the support. These are support calculations, and I'm not going to dwell on this at all, except to point out that the short-term loading is relatively benign, but we were concerned about the long-term loading here, and we decided that the most logical way to do this was to calculate the size of the plastic zone and degrade all of the material in the plastic zone basically to a soil, so that over a period of 100 or whatever years, we said that we have to be able to cater for that type of loading, and the points up here are the long-term load points thrown onto the support. I'm not going to make it in 15 minutes, but I'm going to be pressed. This is what the tunnel looks like when it's properly constructed, and as I say, it's all the way through now, but at the moment, work is going on looking at what the requirements are to put the tunnel back into operation, because some of that tunnel is now 30 years old and it's not in great shape. What you see here is a record from as constructed geological information, where the engineers on site have gone back and recalculated the anticipated deformations and plastic zone size. And here you have superimposed areas of known problems. And they're going systematically through this, looking at areas that they've got to fix, obviously, because they're broken, or that need further investigation, where they would at least go in and do some drilling to find out if the shotcrete was really what you think it is, and whether things are going to be in order for long-term operation. We expect that process to take about 2 years before the tunnel is finally ready for water transmission. So to conclude, when the strength of the rock mass surrounding a tunnel is exceeded, it will fail. And you can't do anything about that. That's a fact of life. What you can do is, if you intelligently design support systems following the principles that we've talked about so far, and we'll talk about in this conference, you can control that failure and still build useful, safe, and effective tunnels. The key is maintaining this shape of the tunnel. So if you construct a tunnel, don't let it run away from you. Try and maintain the shape. That's a lot easier said than done, because as John Hudson pointed out, or as Ivan pointed out earlier on, if you hit a cast stone filled with garbage, unexpectedly, it's difficult to maintain the shape. And finally, that while you can do all the analysis you like, it's the behavior of the tunnel itself that's important, and so monitoring and back analysis becomes an essential part of the design process. This must be a continual feedback loop so that you can incorporate the lessons learned as you progress. And then finally, Professor Paul Marinos, who's my co-author here, and I worked together to add an addendum to the paper, which is just a little addition on some observations from experience of what different rock masses might contain in their makeup. So thank you for your attention. I'm sorry that I've had to go through this so quickly, but I'm trying to help the organizers keep at least closely on time. Thank you.